Is the Cascadia Megaquake closer than we think? If the LA wildfires have taught us anything, it's that disaster is no longer a question of if, but when. Now, northwest of the fire-damaged areas lies an even deadlier force of nature, the Cascadia Subduction Zone. For centuries, tension has been building beneath the Pacific Northwest. Experts warn this sleeping giant could unleash a magnitude 9.0 earthquake. The aftermath? A tsunami capable of obliterating coastal towns, crippling Washington, Oregon, and Northern California, and leaving millions stranded. In 1700, this fault line created ghost forests of millions of dead trees and tsunamis that crossed the Pacific. Today, the stakes are higher than ever, with lives and hundreds of millions of dollars in infrastructure on the line. Is the Cascadia Megaquake closer than we think? Join us as we break down the signs, the science, and what it means for the Pacific Northwest. On January 27, 1700, Japanese chroniclers documented something terrifying: a massive wave that smashed into the island of Honshu, leaving destruction in its wake. But here's the strange part: this orphan wave had no apparent parent earthquake nearby. Instead, the culprit was an enormous quake that struck 12 hours earlier and more than 7,000 kilometers or 4,350 miles away near Vancouver Island. Entire villages belonging to the Hawaiian First Nation were wiped out as people slept, unaware of the looming danger. Fast forward 300 years to 1986, when paleontologists discovered a ghost forest along Washington's coast, hundreds of trees suddenly killed by saltwater inundation. These mysterious clues all pointed to a single event: a massive earthquake along the Cascadia Subduction Zone. This zone is where the Juan de Fuca tectonic plate grinds under the North American plate, creating immense pressure. Geologists have meticulously analyzed soil layers, estuaries, and tidal flats across the Pacific Northwest, uncovering a timeline of 40 massive earthquakes in the last 9,850 years. That's an average of one quake every 246 years. Now, what's scary is that the last big one struck 324 years ago. You do the math. We're 78 years overdue. That means it's probably closer than we think. And if it hits, FEMA predicts a 9.0 magnitude earthquake in Cascadia could be the deadliest natural disaster in North American history. Entire communities could vanish. Cities along the coast would be torn apart, and a tsunami would leave little chance for escape. The potential death toll is staggering unless steps are taken to prepare. The Cascadia Subduction Zone isn't just a geological curiosity, it's a ticking time bomb. So what's the key factor that could mean the difference between life and death? Stick around, because this knowledge might just save lives. But to begin, let's establish some very important context. The United States sits on some of the most tectonically active real estate on the planet, nestled between the Pacific, North American, and Caribbean plates. These massive slabs of rock constantly grind, shift, and collide beneath the surface, creating a recipe for catastrophic earthquakes. From the notorious San Andreas Fault in California to the new Madrid seismic zone in the Midwest, the U.S. is crisscrossed by fault lines capable of altering the landscape in seconds. But one fault zone, often overshadowed by its more famous counterparts, is the Cascadia Subduction Zone. This geological giant lies off the west coast, stretching from Northern California to British Columbia. It's where the Juan de Fuca and Explorer plates dive or subduct beneath the much larger North American plate. The result? A region primed for what's known as mega-thrust earthquakes, some of the most powerful quakes on Earth. The Cascadia Subduction Zone isn't just one fault, it's part of a complex web of tectonic activity. Along the primary subduction interface, smaller strike-slip and normal faults add to the seismic risk. The main fault zone itself runs about 620 miles or 1,000 kilometers along the Pacific Northwest coastline, where oceanic plates are relentlessly pushed under the continent. Here's how these quakes work. Over centuries, the Juan de Fuca and Explorer plates inch their way beneath North America, generating immense pressure as they're forced together. This strain builds until the plates suddenly slip, unleashing a devastating earthquake. Cascadia's megathrust quakes can reach a magnitude of 9.0 or higher, powerful enough to rank among the largest in the world. That's not just numbers on a scale. It's the kind of force that could reshape cities and spawn tsunamis across the Pacific. Cascadia isn't alone in the seismic drama. To the south, the San Andreas Fault snakes along the California coast, capable of producing magnitude 8.0 earthquakes. Meanwhile, the basin and range region further inland features normal faults created by the stretching and thinning of Earth's crust. Combined, these systems make the western U.S. a seismic hotbed. Scientists keep a close eye on Cascadia using a network of seismometers and GPS stations. These tools capture the region's every tremor, helping researchers piece together its complex geology. Geological records like tsunami deposits and evidence of sinking coastlines reveal that major Cascadia quakes happen roughly every 300 to 600 years. The last big one struck in 1700, leaving a trail of destruction and a tsunami that reached Japan. Now, over 3 centuries later, the clock is ticking. Tectonic strain continues to build along the fault, and experts warn there's a high chance of a magnitude 7.1 or greater earthquake hitting the region in the next 50 years. If that happens, the effects would be catastrophic. Coastal towns could face intense shaking, landslides, and a towering tsunami that would devastate communities from Northern California to Vancouver Island. The Cascadia Subduction Zone may not grab as many headlines as the San Andreas Fault, but its potential for destruction is unrivaled. But here is what most people do not consider. The most terrifying aspect of these earthquakes isn't the ground shaking, the buildings collapsing, or the chaos they bring, but the tsunami. Understanding how these massive waves form might just be the biggest lifesaver. Now, let's break down how these tsunamis actually work. Unlike wildfires, floods, or volcanoes, large subduction zone earthquakes are rare. But when they do happen, they unleash tsunamis capable of traveling at the speed of a Boeing 737. That's over 500 miles per hour or over 805 kilometers per hour. And no, these aren't waves you can simply ride out. Typical ocean waves are created by wind, like when you blow across the surface of a hot cup of coffee and see ripples form. Now imagine you don't just blow on the coffee, but slam the cup down on the table. That jolt displaces the liquid, sending waves surging outward. A tsunami works similarly, but on an unimaginable scale, triggered by a sudden shift in the ocean floor that lifts the entire column of water above it. These waves aren't just big, they're relentless. Their wavelengths stretch for miles, and their arrival can be deceiving. From the shoreline, a tsunami might look like it's rolling in slowly. Many assume they have time to act. But before they realize it, the wall of water accelerates as it hits land, crashing onto the shore with devastating force. Every coastline on Earth is vulnerable to tsunamis, but certain regions face heightened risks. Take the 2004 Sumatra earthquake and tsunami, for example. A colossal 9.1 magnitude quake sent waves as high as 100 feet racing across the Indian Ocean, ultimately killing over 230,000 people. We'll unpack the lessons from that tragic event and how to prepare for the impending doom later in the video. So, tsunamis are triggered by landslides, volcanic eruptions, or even meteor impacts. But the most common culprit? Earthquakes. And not just any earthquakes. The giants born in subduction zones, also called megathrust earthquakes. These occur along fault lines where tectonic plates collide. The idea of tectonic plates might seem like ancient knowledge, but it wasn't formally accepted until the 1960s. Picture Earth's crust as a cracked eggshell, with each piece, these plates, floating on a hotter, semi-molten interior. Sometimes these plates clash, and when one dives beneath the other, a subduction zone forms. Earth's story starts with fire. 4.5 billion years ago, the planet was a blazing inferno. It's still cooling today, with tectonic plates as its cold outer rind. As they cool, plates sink slowly back into the planet, while hotter material rises to the surface, a process akin to a spherical lava lamp. This cycle moves at a snail's pace, about an inch or two per year, roughly the speed your fingernails grow. But here's where things get dramatic. As these plates move, friction keeps them locked at their edges. They're still trying to push past one another, building up stress inch by inch, year by year, sometimes for centuries. Imagine 300 to 400 years of movement, several hundred inches, stored up like a wound spring. Eventually, the rocks can't take the strain anymore, and when they snap, it's catastrophic. That's the earthquake. The sudden release of energy shakes the ground, topples buildings, and, if it occurs underwater, displaces vast amounts of water, triggering a tsunami. These waves of destruction ripple outwards, wreaking havoc across coastlines. Subduction zones are scattered across the globe, but they're concentrated along the Pacific Ocean's infamous Ring of Fire. This region alone accounts for more than 80% of all tsunamis. One area drawing heightened attention is the Cascadia Subduction Zone off the U.S. West Coast. For years, scientists underestimated its potential. Now they recognize it as a sleeping giant capable of unleashing devastating earthquakes and tsunamis, on par with the most catastrophic events in recorded history. Now, to give you an idea of what this means, let's take a look at the massive 9.1 magnitude quake that sent waves across the Indian Ocean in 2004. And there's a lot about this event that scares experts when considering the impending Cascadia Megaquake. Tsunamis rank among the most devastating natural disasters, capable of wiping out entire communities in a matter of moments. But one of the most devastating cases in modern history is the 2004 Indian Ocean tsunami, which unleashed waves towering up to 100 feet tall. Within hours, the disaster claimed the lives of approximately 230,000 people across 14 countries, cementing its place in history as one of the deadliest natural calamities ever recorded. Unlike the waves we associate with winds or the gravitational pull of the moon, tsunamis are born from colossal displacements of water. In the case of the Indian Ocean tsunami, the trigger was a staggering 9.2 magnitude megathrust earthquake beneath the sea. This Boxing Day tsunami occurred along a 1,600-kilometer, roughly 994-mile subduction zone, where the Indian plate slid beneath the Burma plate. As strain built over time, the overriding plate bulged and eventually slipped, releasing an almost incomprehensible amount of energy. The resulting tectonic uplift displaced an estimated 30 cubic kilometers of water, unleashing waves with an energy equivalent to 5 megatons of TNT, more than double the explosive force used in all of World War II. On average, 2 tsunamis strike the world each year, with a highly destructive one occurring once every 15 years. So what made the 2004 event uniquely catastrophic? For one, it was the earthquake's proximity to land coupled with the extraordinary speed at which tsunamis travel. The quake's epicenter lay just 160 kilometers, around 99 miles off the western coast of northern Sumatra. A mere 20 minutes after the earthquake, waves began battering Sumatra's shores, claiming nearly 100,000 lives almost instantly. 90 minutes later, the tsunami reached Thailand, inflicting similar devastating losses. These waves traveled outward from the earthquake's epicenter at speeds of up to 805 kilometers or 500 miles per hour, comparable to a commercial jetliner, leaving little chance for escape as they surged inland with unparalleled ferocity. Another key factor was the absence of a warning system in the Indian Ocean. While there was a narrow window of time between the earthquake and the tsunami's arrival, no effective alert system existed to notify those in its path. This lack of preparedness meant entire populations were caught off guard. Even today, tsunami detection remains a challenge, especially in deep waters where disturbances are often subtle and go unnoticed. At sea, a tsunami might appear as a low, broad swell, barely perceptible even to passing ships. However, as the wave approaches shallow coastal waters, It slows, gains height, and transforms into the towering, destructive force we associate with tsunamis. The first sign of an impending tsunami is often the earthquake itself. But complicating matters is the fact that tsunamis can strike thousands of kilometers away from their source. Earthquake sensors alone aren't always enough, particularly when tsunamis are caused by underwater landslides or volcanic eruptions, which don't always produce easily detectable seismic activity. In such cases, the lack of a robust detection system can prove fatal. Analysts have long argued that the devastation of the 2004 tsunami could have been significantly mitigated if a warning system like the one in the Pacific Ocean had been in place. Today, tsunami warning systems have improved, but they're far from foolproof. Deep ocean assessment buoys, seismic monitors, and coastal alarms are part of the global effort to predict and prepare for these disasters. However, challenges remain, especially in regions where resources for such systems are limited or where the population is unfamiliar with tsunami preparedness protocols. While strides have been made, it's clear that even with the best technology, the unpredictable nature of tsunamis makes them a formidable threat. The 2004 Indian Ocean tsunami was not just a tragedy, but a wake-up call to the world about the power of nature and the critical need for preparedness. As we look ahead, one question lingers. Are the warning systems we rely on today enough to protect us from another disaster of such epic proportions? We will dive deeper into how these systems work and whether they can truly stand up to the fury of the sea in a moment. For now, though, imagine the sheer scale of a 9.0 magnitude earthquake and what might happen if a similar event occurred closer to home along the Cascadia Subduction Zone. The 1700 Cascadia Megathrust earthquake stands out as one of the most destructive events in North American history. When it struck, the ground tore apart, unleashing a tsunami that soared as high as 100 feet. This wall of water obliterated indigenous villages along the Pacific coast, from California to British Columbia. The chaos didn't stop there. The tsunami raced across the Pacific Ocean, reaching Japan. The Japanese, stunned by the sudden onslaught, called these orphan waves. There had been no warning, no trembling ground, no reason to run. It was a mystery they couldn't solve at the time, but they recorded everything: the wave heights, how far inland the water reached, and the devastation it left behind. Centuries later, those records, meticulously kept during Japan's Edo period, revealed the truth. No earthquakes were reported in other seismic hotspots like Kamchatka, Alaska, or Chile. The only plausible source of the tsunami was Cascadia. By combining historical accounts with geological evidence, scientists pieced together the story. The Cascadia earthquake caused the devastating waves that struck Japan's shores. While Japan had written records, the indigenous peoples of the Pacific Northwest preserved their history through oral traditions. One of the most famous stories is the War of the Thunderbird and the Whale. The legend speaks of a night so dark and stormy, it felt like the end of the world. Thunderbird, a mighty creature with enormous wings, soared silently through the storm clouds. She swooped down and snatched up Whale, her ancient rival. Higher and higher she climbed until she released him. When Whale slammed into the earth, the world shook violently. That's when the ocean withdrew, leaving the shoreline bare. For those who knew the signs, it was a warning. The wise ones grabbed their canoes and paddled to safety. Moments later, the ocean returned with a vengeance, swallowing villages whole. Survivors spoke of canoes stranded in treetops and a landscape forever changed. The Thunderbird and Whale story isn't the only legend tied to that night. On Vancouver Island, the Huayot people told of dwarfs living inside a sacred mountain. A man invited to dance around their drum accidentally kicked it, trapping the drum's sound in its foot. Each step he took outside the mountain made an earthquake, causing floods and destroying their villages. Further south, the Yurok people of Northern California believed a being named Earthquake was to blame. With feet so heavy they cracked the earth, he ran wild that night, shaking the ground and pushing the ocean inland. As the waters rose, the Yurok climbed a hill and danced to drive him away. But when they returned, their homes were gone, lost beneath the floodwaters. These stories, passed down for generations, attempt to explain what happened. Whether it was Thunderbird, earthquake, or some other force, one thing is certain: the earth shook, the sea rose, and life along the coast was forever altered. It wasn't until centuries later that scientists connected the dots. The 1700 Cascadia earthquake and the tsunami in Japan were part of the same event. This wasn't just a local catastrophe, it was a global disaster. But modern scientists were on the hunt for solid proof of this catastrophic event, which sparked quite a saga. Eventually, they found what they were looking for. For decades, Native American legends and Japanese records of catastrophic events tied to the Cascadia region were dismissed by the scientific community. These stories, once thought to be myths, began to take on a new significance in the 1980s. That's when geologists turned their attention to the Cascadia Subduction Zone, a seismic fault lying just off the Pacific Northwest coast. In the late 1980s and early 1990s, geologist Brian Atwater and biologist David Yamaguchi conducted groundbreaking research that forever changed how we view this fault line. Their work revealed a history of massive earthquakes, proving the Cascadia Subduction Zone was far more dangerous than anyone had imagined. Atwater's findings in particular sent shockwaves through the scientific community, exposing the immense risk faced by over 13 million residents in the region. Atwater's research uncovered clear evidence of past megaquakes buried in the landscapes of the Pacific Northwest. By studying soil layers, tidal zones, and even the growth rings of ancient trees, he pieced together a story of destruction and renewal. Three key indicators stood out: sudden land subsidence, where the ground abruptly sinks, layers of sand trapped beneath mud in coastal estuaries, and signs of severe stress or death in trees. These clues all pointed to massive earthquakes caused by the collision of tectonic plates beneath the Cascadia region. Two pieces of evidence in particular stand out. The first is the sand layers found in estuaries along the Pacific Northwest coast. These aren't ordinary sand deposits. They're the remnants of tsunamis triggered by massive earthquakes. When a tsunami hits the land, it carries sand and debris from the ocean, depositing it over the muddy tidal zones of rivers and wetlands. Over time, new layers of mud build up, covering the sand, and the cycle repeats with each earthquake and tsunami. Atwater's team found these sand layers in nearly every estuary, from small creeks to massive rivers like the Columbia, creating a timeline of tsunamis stretching back thousands of years. The second piece of evidence is found in ghost forests, eerie stands of dead trees in low-lying coastal areas. These trees tell a story of sudden environmental change. During a major earthquake, the land sank, causing salt water to flood the forest and kill the trees. The remains of these trees, some still standing centuries later, match the timeline of the 1700 Cascadia earthquake, a massive event that sent a tsunami all the way to Japan. Together, the subsidence, tsunami sand layers, and ghost forests paint a vivid picture of the region's seismic past. Atwater and his team identified evidence of 40 major earthquakes in the Cascadia Subduction Zone over the past 9,860 years. On average, that's one every 246 years. But here's the catch: the intervals between quakes vary wildly, from as little as 27 years to as much as 577 years. The last megathrust earthquake hit in 1700, 324 years ago. By the averages, the Pacific Northwest might be overdue for another big one. But predicting these events is anything but simple. Statistically, the odds are sobering. There's a 14% chance of a magnitude 9 earthquake, a full rupture of the Cascadia Subduction Zone by 2050. For a magnitude 8 earthquake, the odds jump to 37%. A magnitude 9 quake would devastate the entire region, while a magnitude 8 might rupture just part of the fault, potentially targeting northern areas near Vancouver or southern sections in Northern California and Southern Oregon. While averages provide a sense of timing, they don't capture the unpredictability of nature. Now, let's return to the Pacific Northwest and explore the possibilities for minimizing the impact of natural disasters as well as the current situation. Just for context, in 2023, a magnitude 7.8 earthquake devastated Turkey, killing over 60,000 people. The tragedy wasn't just about the quake's power, it was about poorly built structures that couldn't stand the pressure. While the Pacific Northwest boasts better construction standards, many buildings still lack seismic retrofitting. If a massive earthquake struck, plenty of them would crumble. The good news? A full-scale rupture, though possible, isn't as likely as a partial one. A partial rupture would still be intense, with magnitudes ranging from 7.6 to 8.6, but it wouldn't match the catastrophic destruction of a magnitude 9 quake. Plus, there's progress being made to prepare for such events. And then there is the National Tsunami Warning Center, managed by the U.S. National Oceanic and Atmospheric Administration, or NOAA. This is the world's leading tsunami warning system, and it primarily monitors the Pacific Ocean, a region highly vulnerable to tsunamis thanks to the infamous Ring of Fire. At the heart of this system is DART, short for Deep Ocean Assessment and Reporting of Tsunamis. This innovative technology can detect tsunamis in real time and provide accurate forecasts. Here's how it works. Each DART station has three main components. First, a pressure recorder sits anchored on the ocean floor, constantly measuring water pressure. Since water pressure directly relates to the height of the water column above it, any changes can indicate unusual activity. Second, a surface buoy floats above, connected to the recorder by an acoustic link. Lastly, this link allows data to travel between the seafloor and the surface in real time. When everything's normal, the system quietly measures water pressure over time. But if a giant wave, say the early stages of a tsunami, passes over the DART station, the increased water pressure triggers the alert process. The recorder sends an alert to the surface buoy via acoustic signals. From there, the buoy transmits the warning to a satellite, which relays it to the Tsunami Warning Center for analysis. If the system confirms a tsunami, emergency alerts are sent out through text messages, emails, and other systems, giving people time to evacuate to higher ground. Currently, about 40 DART stations are scattered around the Pacific Ocean's Ring of Fire. There are also stations in the Caribbean and along the Atlantic coast. Thanks to the system's success, other regions have adopted similar technologies. After the devastating Indian Ocean tsunami in 2004, the Indian Ocean Tsunami Warning System was established in 2006. Today, it includes 7 DART stations. Australia's Joint Tsunami Warning Center operates 5 stations, while South America has 8. These systems work independently but frequently share data, creating a global network that aims to warn populations as quickly as possible. Despite all these advancements, the clock is ticking. If the big one were to strike the Pacific Northwest tomorrow, the outcome would be catastrophic. But if this catastrophe is delayed for a decade or two, ongoing improvements in building standards and warning systems might just tip the scales in favor of survival. While natural disasters can't be prevented, they can be prepared for, and preparation makes all the difference. This is where we should call it a wrap. But there's something we didn't mention in this video, and that is that the Cascadia Megaquake isn't the only natural disaster we should be concerned with this year. We made this video. More earthquakes in the new Madrid Fault. What's going on? You don't want to miss that.